All right, so we know that this is less than 7. And it's about discontinuities in the graphs of piecewise defined functions. All right. So we're just going to graph these 3 scenarios right here. So the pieces can connect at a closed circle at x is equal to a. So let's just say we have our xy coordinate. And we'll call this a. Let's say we have a absolute value function and then a quadratic function. So these 2 functions meet when x is a, all right? When x is a, we have an absolute value function and then a quadratic, okay? In the second box, it says the pieces can connect at an open circle when x is equal to a. So we have our xy coordinate again. My x coordinate, my y coordinate. Here's a. We have an absolute value function, a hole, and then our quadratic. Okay? So the piece can connect at an open circle at x is equal to a. All right? But in order for this to be continuous, we have to have another point somewhere along when x is a. So let's put a point right here. So here we have a point of a y value that makes a defined. Okay? And then in the third box, it asks us the pieces cannot connect with each other at all at x is equal to a. So let's say we have our xy coordinate, same a value, my absolute value function, all right? And let's say we have a point here, and then we have a hole with a quadratic, okay? Is our function defined? Yes, it is, because of the point in the absolute value function, okay? Because of the point in the absolute value function. All right, and then everybody got this written down? Good deal. And the next, we are given 2 equations for q of x, all right, and we want to graph them, and we're going to have to ask, it's going to ask us some questions about it, okay? So it says the latter 2 of these 3 scenarios are examples of functions that have discontinuity. Before we take a look at graphs that have discontinuities, let's investigate one function in which there is no discontinuity. That is a function whose pieces connect at a closed circle, all right? So q of x, all right, we have negative x plus 3 squared plus 4 when x is, or when negative 5 is less than or equal to x, or greater than or equal to x, but less than 0. Okay, so what happens when x is negative 5? No, because it's equal to. Okay, and what would that y value be? Well, let's see. Negative 5 plus 3 is 2. Negative 2. Negative 2 squared is 4. Negative 4 plus 4 is 0. So we have negative 5, 0. And then we have negative 4. Negative 4 plus 3 is 1. Negative 1 squared is 1 times negative. Negative 1 plus 4 is 3, right? When in doubt, draw your table. And then here we have a vertex at negative 3, 4. And then it just mirrors the first, all right? And then what happens when x is 0? 3 squared is 9. Negative 9 plus 4 is negative 5. So here we will have a hole. So here's what our quadratic will look like. All right. And then now we have an absolute value function, correct? So I know that I'll have a vertex at 2, negative 7. So what happens when x is 0? Well, 0 minus 2 is negative 2. Absolute value of negative 2 is 2. 2 minus 7 is negative 5. So what happens to our piecewise function now? Is there a hole? Nope. So is this graph continuous or discontinuous? Well, let's see. So the first piece of the graph Q of x will end just shy of x being equal to what? So remember, there was a hole.
Please come to the front.
There was a hole when x was what in the first piece of our piecewise function? When x was 0. And where did our where did the absolute value function begin in the second equation? What is the restriction? X has to be what? Greater than or equal to 0. So in the second piece of Q of x will begin at x is equal to 0. So it asks us, is Q of x defined at the x value where the first piece ends and the second piece begins? If so, find the y values of y at that x value, okay? So we got to find Q of 0, all right? But look back at the piecewise function. Do we have to use equation 1 or equation 2? Are you sure? Equation 1 or equation 2? Equation 2. Why equation 2? Well, look at x has to be what? Less than or equal to 0. In the first equation, x has to be least than 0. Or less than 0. It can't be equal to 0. Whereas in the second equation, it can be 0. So we have to use the second equation. And then we get 0 minus 2 minus 7 is equal to 2 minus 7, which is negative 5. All right? Negative 5. Now it asks us to complete the following statements according to the graph. Okay? Now, this notation, it says as of x approaches 0 with the little minus sign up here. Okay? What that interprets is, what is as x is 0, what is it approaching, talking about the y value, what's it approaching to the left? So it's decreasing from the left, and it's approaching what? Negative 5. The right side of, as x approaches 0 to the right, the graph approaches what? Negative 5 as well. So here we have negative 5 and negative 5. Then it asks us to, using the equation of Q of x, determine the y values that each piece approaches from the left and the right as x approaches 0. So let's do that. So as x approaches 0 to the left, all right, we have Q of x being equal to, well, if we're approaching Q of x to the left, then we use the quadratic equation. So we have negative 0 plus 3 squared plus 4. All right? Yes. Come over where you can see, because I'm recording on my iPad. So as x approaches 0 to the left, Q of x will then be negative 5. All right, we solved that a while ago. And as q of x approaches 0 to the right, we have to use the absolute value function. We have q of x being 0 minus 2 minus 7. And what do we get? What do we get? Negative 5, right? And since both of these pieces approach the same y value of negative 5, and q of 0 is equal to negative 5, then q of x is continuous at that x value when x is 0. Okay? So we could say since both pieces approach the same y value of negative 5 and g of, or q, excuse me, of 0 being negative 5, then q of x is continuous at x being 0. Everybody have this written down? All right, let's move on to this right here.
Elena Green, please come to the student entrance.
All right, so there are two different types of discontinuities, all right? There's a jump and a point, okay? A jump and a point. When you have a jump, two pieces they're not connected. And when we have point, you have two pieces connect at an open circle. So 2 points that do not connect, and then 2 points connect at an open circle. All right? So as you're getting that written down, look at these four functions, okay? We have f of x, g of x, h of x, and p of x, okay? And they were so nice enough, they went ahead and graphed these functions for us. So we're not going to spend much time looking at the graphs right now. We're going to go ahead and look at the next page and identify what type of discontinuities we have, all right? So let's go ahead and let's move to page 59. All right, and we're looking at f of x, okay? We're looking at f of x. And it asks us what type of discontinuity occurs in the graph of f of x at what x value does it occur? So look at the function f of x. Okay? And what type of discontinuity occurs in f of x? This is what we call a jump at what x value? Okay? So we have an x value that's equal to 3, all right? And this is a jump discontinuity. Now, here's the million-dollar question. This is what we want to figure out. Is f of x defined at this x value? If so, what is the y value? All right, so we want to know if f of 3 is defined. If it is defined, what's my y value? Okay, so look at f of 3. Is this function defined when f is 3? No, why not? Because we have holes at both piecewise functions, correct? So when f is 3, our function is undefined. All right, it is undefined. Okay, does anybody have any questions? All right, moving on to the next box. By investigating the constraints of the equation, the first piece of the graph of f of x will stop just shy of x equaling 3. Okay, that's where our hole begins in our absolute value function. And the second piece of f of x will begin just past x being equal to 3. All right, and that is where our linear equation starts. All right. So, Cam, as x approaches 3 to the left, okay, the graph of f of x approaches what y value? As we're looking, okay, so we're looking at f of x. This is f of x. All right, and we're looking at the function that's to the left, so the absolute value function. As we approach x being equal to 3, what is my y value? 2. Good, very good. And as x approaches 3 to the right, the graph of f of x approaches what y value, Jason? 4. Okay, 4. So let's see what happens here. So it asks us, using the equation of f of x, determine the y values that each piece approaches from the left and the right of x equaling 3. So we have as x approaches 3 to the left, so we have f of x is 3 plus 3 minus 4. That is the equation for the absolute value function of f of x. So what's 3 plus 3 minus 4? 2. Okay, it's 2. And what about when x approaches 3 from the right? Well, if it approaches it from the right, is that our linear equation? Yes, it is. So negative 1/3 times 3 plus 5 is negative 1 plus 5, which is just positive 4, right? So, since both pieces approach different y values, then f of x has a jump discontinuity So jump discontinuity at x being equal to what? Very good. So in g of x, what type of discontinuity do we have? No. We're still looking at g of x. A jump at what x value? X being -3. Very good. Okay. Then it asks us, is g of x defined at this x value? If so, what is the y value? All right. So we want to find g of -3. Now, we have some restrictions here. Which equation am I going to have to use for g of x? When can x be equal to -3? In the quadratic or the square root function? In the quadratic. So we have -3 plus 6 squared plus 7. All right? And then we get -3 plus 3, or -3 plus 6 is 3. 3 squared is 9. -9 plus 7, we get what? -2. Very good. -2. All right. And by investigating the constraints of this equation, the first piece of the graph of g of x will stop when x is equal to -3. And the second piece of g of x will begin just past x being equal to -3. Okay? But the next section asks, what is g of x? What does g of x approach as x is being approached to -3 on the left? All right, and what about 3 from the right? -4. Okay? So what that means is, it asks us, using the equations of g of x, determine the y values that each piece approaches from the left and the right of x minus 3. So as x approaches -3 to the left, g of x is -3 plus 6 squared plus 7, and we found that to be -2. And as x approaches -3 from the right, we have g of -3, it should be -3, not x, being equal to -3 plus 3 minus 4, and we get -4. All right. So here we have different y values, right? Different y values. And since both pieces have different y values, then g of x has a jump discontinuity at x being equal to what? -3, right? All right, so here we're looking at h of x, and what type of discontinuity occurs in the graph of h of x, and at what x values does it occur? Okay, so we have a what type of discontinuity at h of x? a point, and what's my x value? -1, okay? Now, it asks us, is h of x defined at this x value? If so, what is the x value? So, is our function defined when x is -1? No. Why is it undefined? Because it is a whole. Very good. It is undefined. Okay? So by investigating the constraints of the equation, the first piece of the graph of h of x will stop just shy of x being -1, and the second piece of h of x will begin just past the x value being equal to -1. All right? So -1 and -1. So as x approaches -1 to the left, what is my y value? Try again. 1. And what about when we approach h of x from the right? It goes to 1 as well. All right? Now, it then asks us, using the equation of h of x, determine the y values that each piece approaches from the left and the right. Okay? Well, the only thing we have to do is substitute our x values in for our two functions. The first one's the absolute value function, and the second one's a quadratic. So as x approaches -1 from the left, we have h being equal to h of -1 equal to -1 plus 4 minus 2. -1 plus 4 is 3. Absolute value of 3 is 3. 3 minus 2 is 1. And as x approaches -1 from the right, h of -1 is equal to -1 plus -1 minus 1 squared plus 5. -1 minus 1 is -2. -2 squared is 4. -4 plus 5 is 1. Okay? So since both pieces approach the same y value, and our y value is 1, but what happens when our x value is -1? Look at the restraints on h of x. X has to be what in the first equation? Look at the equation for h of x on page 58. X has to be less than -1. And then in the second equation, x has to be greater than -1. So, can x be -1? No. So, this does not equal 1. Then h of x has a what type of discontinuity? Point. So we have a point discontinuity at x being equal to -1. All right, let's go ahead and move on to P of x. So it says, what type of discontinuity occurs in the graph of P of X at what X value does it occur? So P of X, we have a point. And at what X value? Okay. And then what is our function when X is -3? -2. -2. You see that solid point? Okay. So by investigating the constraints of the equation, the first piece of the graph will stop just shy of X being -3. And this should be the third piece, not the second. And the third piece of P of X will begin just past -3 because we do indeed have that point. All right. As X approaches -3 from the left, the graph of P of X approaches what value? What Y value? Okay. And as X approaches -3 from the right, the graph of P of X approaches what X value? Say it again. Should be +2, okay? Because at that point, all right, that's not our graph. That's just a point, right? It's just a point. Now, using the equation of P of X, determine the Y values that each piece approaches from the left and the right, okay? So as X approaches -3 from the left, okay? P of -3 is equal to 1/3 -3 plus 3, which is just positive what? 1/3 times -3 is -1. -1 plus 3 is 2. As X approaches -3 to the right, P of -3 is equal to -3 minus 1 minus 2, which is +2. Okay? So, check this out. Since both approach y being equal to 2, but when our function, when x is -3, can it be equal to 2? No, it cannot. That is why we have a what? That is why we have a point discontinuity at x being -3. All right. Moving on. All right, so here it asks us, after investigating the graphs of the equations of q of x, f of x, g of x, h of x, and p of x, by answering the questions about each, what are some general conclusions that you can make about when a function will be continuous at x being equal to a, when there will be a point or jump discontinuities at a? So the first one, when we have a continuity at x being equal to a. Okay? So it's continuous at x being equal to a when both pieces, when they must approach the same y value b, okay? So they're approaching the same y value b, and the function of a has to be b, okay? So in order for it to be continuous, both pieces must approach the same y value, b, and the function of a must be equal to b. All right? When we have a jump discontinuity at x being equal to a, we have both pieces must approach different y values, and f of a may or may not be defined. Okay? So both pieces must approach different y values, and f of a may or may not be defined. Okay? And then what about point discontinuity? Do they both approach the same y value? Yes, because it's not a jump. And two, if it's a point discontinuity, then the function of a, is it equal to b? Nope, it is not.